everyone. In the last session, so we have discussed about the different types of rotors like squirrel cage rotor and slip ring rotor. So along with these two types of rotors, so we have also discussed, we have also learnt about the that is the starter, necessity of starter. Okay. So why should we consider this starter? So what is the necessity of starter? So what happens if the starter is not considered? So these topics we have discussed in the previous session. In this session, we are going to discuss about the working of each starter. Okay. So we have three different types of the starter. So that is by which three-phase induction motor can be started. So one is a direct online method, and second one is auto transformer starter, and next is star delta starter. Okay, so we have three different types of starter, but so we are going to discuss, because out of all these that is most commonly used starter is star delta starter. And one thing you need to remember is, like in all these starter, so initially the less, that is reduced voltage is applied to the winding, especially at the starter, and once the rotor picks up the speed or runs at the normal condition, so later it gets the full rated voltage. So remember, this is the main function of the starter, right? In all these starter, so remember initially, so we have less voltage or the reduced voltage is applied to the that is stator winding, and later once the rotor picks up the speed, okay, and runs at the normal condition or the normal speed, so it gets the full rated voltage. Now we shall see the working of the star delta starter. Okay. So you have three figures here. So this is figure A, figure B, and this is figure C. Now figure A shows the circuit of star delta starter. So, and in this circuit you can observe, so there are three lines. Okay. So it is indicated as three phase, and we have TPST. See, TPST is nothing but triple pole single throw switch, and at this position, so we have two positions you can see. So one is run position and another one is start position, and this switch, okay, there is one more switch called TPDT. So TPDT is nothing but triple pole double throw switch. So here TPST is triple pole single throw switch. Okay. So since we have only one switch operation here, but here since we have two, like that is double switches, it is called as TPDT. So triple pole. Why it is triple pole? Because we have three windings here, so that is from three phase supply. So TPDT, triple pole double throw switch. And as I have already indicated, so we have two positions, so one is run position and another one is start position. And so now we shall see how exactly the starter works. And initially, so remember these, that is the TPDT switch is at the position, that is at the start position. So remember, when it is at start position, so it makes star connection. And so how it becomes a star connection, you can just observe. So there are three windings, and let us call the one end of the winding as A1 and another end of the winding is A2, and similarly, so C1, C2, B1, B2. Okay. And initially when TPDT switch is at start position, so this will be connected to the ground point. So remember, when TPDT is at the position start, okay, when it is at start position, so all these 3 points are connected to the ground point. So remember, so when these three are connected, so that means, see here, look at this flow, and when these three windings are given to the ground point, so what happens, which exactly looks like figure B. So remember, which exactly looks like figure B. And similarly here the motor is supplied with a voltage, that is by closing TPST switch. Remember, so as I have already indicated initially, so TPDT switch at position start, so that means one end of the winding is given to the ground point, and other end of the winding, what about other end of the winding? The motor is supplied with voltage. Okay. So because it needs some voltage, that is supply. So which is supplied with some voltage, that is by closing TPST switch, So when TPST switch is closed here, so what happens? So we get a supply, of course it is three phase supply, and which will be given to this stator part or stator winding. So of course when the supply is given to the stator winding and other end of the winding is given to the stators are given to the ground point. So how exactly it looks like? It looks like star circuit, or it is star connected. See, look at this, all the 3 points or all the 3 windings are given to the ground point and other end of the windings are given to the supply. So which exactly looks like the star circuit or star connection. So in star connection we know that like the voltage which we get at each phase. So because this we call it as phase voltage, isn't it? So you can just recall the difference between the line voltage and the phase voltage. Line voltage is nothing but the voltage which is provided, okay, which is supplied between two lines, right. So that is RBY, between two lines is nothing but line voltage, and the phase voltage is nothing but the voltage which is provided or supplied or which is considered across the line and the neutral point, right. So and this voltage we call it as phase voltage, and this voltage when we measure the voltage between R to B, that becomes line voltage. And as you have already studied the difference between the line voltage and the phase voltage, or the relationship between the line voltage and the phase voltage in 3 phase circuits. So VL is equal to root 3 VPH. Then what is VPH here? VPH is equal to, it becomes VL divided by root 3. Right. So VPH becomes VL divided by root 3. So what voltage do we get here? Even though we have the line voltage which is supplied by this 3 phase supply, that is from the source, but the voltage what we get across the that is across each phase or across this load, so that is VPH is equal to VL divided by root 3. So the phase voltage will be reduced. Remember, the voltage which is supplied initially, that is at the starting point, will be reduced since it is star connected, and later once the motor so picks up the speed, okay. So once the motor picks up the speed, or like when it runs at the normal speed or the normal condition, normal speed, so what happens? It gets the full rated voltage. How it gets the full rated voltage? So remember, once the motor runs at the normal speed, or once it picks up the speed, so here the TP/DT switch is thrown, or it can be thrown to the run position. So initially it was at the start position, and once the motor picks up the speed, okay, or it runs at the normal speed or normal condition, when it is working at the normal condition, the TP/DT switch is, okay, thrown to this run position. So when it is thrown to run position, so what happens here? So you can just observe here, now we have this A1, right. So when it is connected to, when this point is connected to, when it is thrown to run position, so this will be connected to A1 point, will be connected to this point, right, which is exactly of course connected to C2 point. So the same thing you can observe here. So A1 is given to C2. So A1 will be connected to C2 point, and further, so you can just observe, of course, so we have C2 here and then C1, then and this point, right. So what is this point called? C1. So later, so C1 will be connected to, which point? That is to B2. So I'll just repeat now. This C1 point is given to, because once TP/DT switch is thrown to the run position, so this will be connected to this point. Then what happens? This C1 point will be connected to B2. So C1 point, so where is C1 here? C1 will be connected to B2 point, right. So initially the A1 is connected to, A1 is given to the C2, of course C1 is given to B2, right. And then, so after this B2, so we have B1, right. So look at this B1 switch, look at this B1 so winding, and at this point, so of course when it is thrown to the run position, so B1 will be connected to this point. So which is this point called? This is nothing but A2. So now B1 is connected to A2. So B1 is connected to A2. What happens when TP/DT switch is thrown to run position? The whole connection, this star connection, becomes delta connection. Initially it was in star connection, okay. So that is like as you have already seen in figure B, so it was in a star connection. In star connection it gets the reduced voltage, isn't it, because VPH is equal to VL divided by root 3. And initially when it is at the star position, that is in star connection, the starting torque. So the starting torque means, again we express in terms of power, so this becomes 1 by root 3, okay, so whole square. So I have just considered this 1 by 3 because the voltage will be reduced by root 3, right? And the starting torque, so as I have already explained, so starting torque will be expressed in the form of power, so which will be again, of course, it is square. Okay, 1 by root 3 square. So what is 1 by root 3 square? So it is 1 by 3. So 1 by 3, and if we just convert this into like in terms of percentage, so it is 33.33%. So remember the voltage, the reduced voltage will be how much, which is again like the voltage will be reduced, the full rated voltage will be reduced to 33.33%. Later, once it becomes, the circuit becomes delta connection, like as I have already explained you how it becomes delta connection. So once it becomes delta connection, then so we get full rated voltage, because so in delta connection we know that VPH becomes VL, right? So once the motor picks up the speed, or when it runs at the normal speed, so what happens? So of course it becomes delta connection, and when it becomes delta connection, this VPH, okay, so phase voltage becomes the line voltage, it gets the full rated voltage. So this is the operation, this is the working of the star delta starter. Next we shall move on to the problems in this chapter. Okay, so first problem, an 8-pole alternator runs at 750 RPM. Okay, and supplies power to a 6-pole, 3-phase induction motor which runs at 970 RPM. Okay, so these are the data provided in the problem. So what is the slip of the induction motor? As I have already explained you in the working principle of the induction motor, so remember F and Ns are the values which are related to rotating magnetic field. Okay, remember, I'll just recall, because once you understand like one problems, then the rest of the problems are similar. So like here F and Ns are the values which are related to rotating magnetic field, because there are two concepts here, there are two speeds here, one is synchronous speed Ns and another one is N, which we call it as the speed of the rotor. Okay, so F and Ns, F is the frequency and Ns is the synchronous speed, and these two values are related to the rotating magnetic field. And similarly F dash and N, similarly, so we have two more values, like F dash and N are the values which are related to the rotor part, so which are related to the rotor, so F dash and N. And now based on this, so we are going to understand the data is given in the problem, and later so we need to simplify this problem. And so look at the problem carefully, an 8-pole alternator. So an 8-pole alternator means, so this is the value of P, so P is equal to 8. And remember, alternator, whenever they provide the values for alternator, so that is to find the value of frequency. Remember here in any problem, if the values are provided which is related to alternator, so that means you need to understand that, so you need to find out the frequency. Okay, so which frequency? That means this alternating frequency F. So P is given as 8 and so runs at 750 RPM. Remember, don't get confused with the speeds here, because there are many speeds. One is Ns and N, and this speed is no more related to, remember this speed. Okay, so 750 RPM, this speed is no more related to Ns and N. So this speed is given which is related to alternator, that is to find the frequency. So once again I will repeat, the speed which is given here, that is related to the alternator. So whenever they provide the values which are related to alternator, that is why, because to find the value of frequency. So P is given as 8, and similarly N is equal to 750 RPM, right, RPM. Okay, and supplies power, later it supplies power to a 6-pole. So now the one more value is given, which is P is equal to 6. So 6-pole 3-phase induction motor. So later from these values later it supplies a power to a 6-pole 3-phase induction motor. So later it supplies a power to 3-phase induction motor which runs at 970 rpm. So remember, which runs at, because the values which are provided here, that is related to the motor, that is related to the rotor part. So 750 rpm, and which is the value of n again. So n is equal to 970 rpm. What is the slip of the induction motor? And so you may be thinking that there are two pole values are given and there are two speed values are given. So as I have already indicated, so the values which are provided related to the alternator means here you need to find out only the frequency. Which frequency? That is the rotating magnetic field frequency. So now how do we find frequency? And we know that F is equal to NP by 120. Okay, I hope you are aware of this equation. F is equal to Np by 120, and substitute these values. So what is N? N is equal to 750 into 8 divided by 120, right? And finally, so you may be getting F is equal to 50 Hertz, right? F is equal to 50 Hertz. And which frequency is this? So frequency of what? So that is rotating magnetic field, F. And later, so we need to find out the value of Ns, isn't it? So we need to find out the value of Ns. So how you can find out the value of Ns? And we know that Ns is equal to, since F is so Ns is equal to 120 F divided by P. So remember, this is the equation, of course. So here F is equal to, always the relationship between the frequency and the speed is F is equal to Np by 120, and similarly Ns is equal to 120 F divided by P. So here you need to substitute the value of frequency of what? Frequency of this. Okay, so it is rotating magnetic field, because we are finding out the speed, that is synchronous speed, which is related to rotating magnetic field. So Ns becomes 120, and of course this is related to what? So this speed is related to the frequency of this F. Okay, and so just now we have calculated the value of F here, so substitute this F. So this becomes 120 into 50 divided by, and so which P you need to substitute? So P is nothing but 6, because again look at the problem. So supplies power to a 6-pole. So now it is providing a supply. Okay, providing a supply to 6-pole. That means 6-pole 3-phase induction motor. So this P is related to the induction motor. So now you need to have P as 6. Right? So don't substitute P as 8, because these two values are given just to find out the value of frequency. So substitute the value of P here and calculate. So Ns is equal to, which becomes 1000, right? So 1000 rpm. Okay, so once you find out the value of Ns, synchronous speed, then so what is the final question? So what is the slip of the induction motor? What is the slip of the induction motor? So what is the equation? You have already studied in the same chapter. We have already derived the expression. So, or we have defined the expression. So slip is equal to, which is the ratio of what? Ns minus N divided by Ns. Okay, which is the ratio of Ns minus N to this Ns. So what is Ns? Ns is equal to, as we have already calculated, which is 1000 rpm minus, and what is N? N is equal to 970 rpm, because remember the supply is given to this induction motor which runs at 970 rpm. So this 970 rpm is nothing but N. So minus 970 rpm divided by again 1000. And so finally if you simplify this, you will be getting 0.03. Right? Or if we express in terms of percentage, so this becomes 3%. So this is how we can calculate the value of slip in 3-phase induction motor. Now we shall look into the next problem, and so read this problem carefully. A 6-pole induction motor. So here I just want to highlight the difference between the previous problem and this problem. Okay, so based on the given statement, a 6-pole induction motor supplied from 3-phase, comma 50 Hertz supply. Okay, so first you need to understand, again I am telling you, so you need to understand the difference between the previous problem and this problem. Here the values which are provided here is 6 pole induction motor, okay, 6 pole induction motor. So now 6 pole which is related to the induction motor supplied from 3 phase, 50 hertz. So directly they have given the value of frequency. So remember, they have provided the value of frequency. So here the initial frequency you need not to calculate. So f is equal to 50 hertz, right? And so P is equal to 6, right? P is equal to 6. Has a rotor frequency. So rotor frequency. So what is rotor frequency? Rotor frequency is f dash. As I have already indicated, so n and f dash are the values related to the rotor, and f and ns. Okay, so f and ns are the values which are related to rotating magnetic field. So here the rotor frequency is given. Rotor frequency is nothing but f dash. So what is f dash? Which is 2.3 hertz. Right. So in the previous problem, so they have provided alternator values. Okay, alternator values, one as P and another one as N. Okay, by using N and P values, so we could calculate the value of frequency. But here, since they have not given the alternator values, of course, since they have directly provided the frequency value, which is again from the 3 phase and which is directly given to induction motor. So remember, they have directly given the value of this induction motor, that is frequency, and another one is P. P is equal to 6. So and they have given f value, P, and then f dash, which is the rotor frequency. And the question is calculate percentage slip. Okay, slip in terms of percentage. So S is equal to f dash divided by f. Alright, so you can just recall this equation. So we have already done this. So S is equal to f dash divided by f. So directly you can substitute the values of frequencies. So here, so what is S, which is f dash? So that is 2.3 gigahertz, 2.3 hertz divided by, and what is the frequency? So frequency is 50 hertz. So f dash is 2.3 hertz and f is 50 hertz. So simplify this expression. If you further simplify this expression, you will be getting 4.6%. So of course, whenever you are expressing this in terms of percentage, so you need to multiply this with 100, then you will be getting this as 4.6%. So as I have already written the answer, S is equal to 4.6%. And then here the speed of the motor. So what is the speed of the motor? So remember, the speed of the rotor or speed of the motor, so both are same. So speed of the motor is nothing but n. So here this is the first part and this is the second part. So we need to calculate the value of n, which gives you the speed of the motor, or we also consider the speed of the rotor. So, and to calculate the value of n, because you know the relationship between this n and ns and s, right? So n is equal to, what is n? N is equal to ns into 1 minus s. So how we have got this equation? We have already derived this expression. How we have obtained this equation? So that is based on the slip equation. So S is equal to, so this we can also, like it is a ratio of ns minus n to ns, right? And if you further simplify this, so you can have the equation as n is equal to ns into 1 minus s. And so here we know the value of s, right? So just now we have calculated, which is 4.6%, that is in terms of percent. And here of course we need to calculate the value of ns. Before we calculate the value of n, so we need to calculate the value of ns, that is synchronous speed. So what is a synchronous speed equation? And we know that ns is equal to, right? So here, because so we know that ns is equal to 120 f divided by p, right? Ns is equal to 120 f divided by p. Oh, and what is frequency here? So frequency you need to have 50 hertz, because remember ns, it is it is related to rotating magnetic field. So Ns and F are the values which are related to rotating magnetic field, and of course you need to consider this frequency, that is 50 Hertz. So 120 into 50 divided by, so divided by P, and which is P here, so P is equal to 6. So substitute the value of P as 6, then so you will be getting Ns as 1000 RPM. 1000 RPM, and substitute these values, that is N is equal to of course Ns is equal to 1000 RPM divided by into 1 minus and what is S? S is equal to 4.6, so that means point so what is S? S is equal to 4.6%. So here this becomes 1000 into, so 1 minus S becomes 0.046, because we have expressed in terms of percentage. So here you cannot have in terms of percentage. So this becomes 0.046. So substitute all the values here, and finally you can calculate the value of speed, and speed becomes 954 RPM. Remember, so unit is very important here. N becomes 954 RPM. So in this way we can calculate the value of slip and the speed of the motor. So now we are done with the 5th module. So we have completed all the 5 modules. I hope you are familiar with all the 5 modules now. Okay, so thanks for your cooperation, and thanks for watching. Once again, thank you.